Professor Lundstrom has been, in some ways, fundamental to microelectronics. One of the fantastic things about microelectronics is it's a relatively young science, so you can actually meet the people who have made a gigantic difference to the industry and your lives in person, and Mark, I would say, is one of these people. Rather than read out the enormous list of his awards, I'll very briefly say that you started off as a scientist and in industry and academia. He then went into numerical modeling of semiconductor devices with rigorous experimental verification and validation. But he then went further and made that available through Purdue, I think it was Punch originally, cloud computing before the term existed. And now NanoHub University, where you can take free classes on nanoscale devices and so on, is also one of his initiatives. So his heart for teaching and teaching at scale is enormous. And if that wasn't enough, he happens to have written a book all the way back in 2006. So I quickly checked, and on Amazon, it's number 21 in optoelectronics, number 71 in semiconductors, and 103 in solid-state physics. And he wrote it in 2006. So this gentleman has actually written the book. Well, he also has a Wikipedia page devoted to himself. So hopefully that should help you kind of place him, as well as being a genuinely nice guy. So, Mark,
all right.
Hand over the microphone.
All right. Well, let's see. I guess I'm already Mike. Thank you. All right. Well, thank you, Matthew, for that nice introduction. It's great to be here. These are exciting times in semiconductors, and I can remember when I was your age. Right? It wasn't that long ago. I took a course when I was a junior called Introduction to Integrated Circuit Engineering. An integrated circuit is a chip, and I thought, this is really cool. And I then did a senior project working in the integrated circuit lab, and I've been involved in this field since my first job out of college and ever since. And most of that time, it was really hard to explain to people what I did, and why it was important. But everything's different today. Everybody understands chips, it seems. Everybody understands that life as we know it would not exist without semiconductor technology. So there is really a whole new era of this technology that's just beginning, and you're all lucky to be here at this time as it's just being re-energized. So if you have trouble hearing me, let me know from the back of the room. So I have a lot of material to cover. This is an incredibly broad industry. It's not only about electrical and computer engineers. Whatever your STEM degree is, there are exciting career opportunities for you. And you will be hearing from speakers from across the entire semiconductor ecosystem. A different one every week will come in. My job is to try to convey to you what the breadth of this industry is all about. So when you have a speaker coming in from a different company, you'll kind of understand where this company fits in the semiconductor ecosystem. So I have a lot of ground to cover. And
it's the button below the button you think it is.
I might have to do it this way, right?
It's the button below the one you think it is. I ran into that as well.
Ah, you're right. Okay. All right. So a little over 2 years ago, the U.S. CHIPS Act was signed, and a lot has happened since then. So this is being described as a once-in-a-generation investment in the nation's future, and it's happening right now. There are three main objectives of the U.S. CHIPS Act. One is to bring more semiconductor manufacturing back. So we learned during COVID that we're really dependent on chips, that there are chips inside everything. And most of these chips were manufactured, we'd outsourced it over the decades. Most of them were manufactured elsewhere. And we learned having these fragile supply chains is really dangerous. So the first priority is to bring more of that manufacturing back. We're going to triple the manufacturing capacity in the US between now and 2032, I believe. The next is, there are areas that the US is leading in. One is the design of chips. We want to maintain our strength, increase our ability in these areas where we're leaders. We're leaders in the development of the sophisticated manufacturing tools that go inside these factories to manufacture chips. But we've fallen behind in the actual manufacturing of leading edge chips. So the leading edge chips, the things that are inside that do all the AI and the cool stuff, 0% of the chips that the U.S., the leading edge chips that the U.S. uses are manufactured in the U.S. And that's pretty dangerous if some things happen. So one of the goals is to reach maybe 28. I think the specific target is that by 2032 we'll be manufacturing 28% of the leading edge chips here in the U.S. And the third goal is to accelerate the pace of innovation. This is a really fast-paced industry. You know, if you aren't paying attention and fall behind, that can happen very, very quickly. The way you stay ahead is by innovating, inventing more quickly than your competitors. So a major goal is investments in R&D and increasing the pace of innovation. All right, so I'm going to cover a lot of ground. Just some definitions. This field is sometimes referred to as microelectronics, and that's the design and manufacturing of complete electronic systems on a small semiconductor chip. So the material is a semiconductor. The atoms, sort of the basic building blocks of everything, is something called a transistor, and they have critical dimensions that are really, really small these days. And let me show you, this is a transistor. You can come down, it's got 3 wires, and it's inside this tiny little package. You can come down and see this afterwards. A leading edge chip could have 100 billion or more of these on a single chip that's maybe 1 inch by 1 inch. So these things are much, much smaller than this, unbelievably small. All right, so what's a semiconductor? So you all sort of understand what a metal is. Metals conduct electricity, gold, copper, aluminum, things like that. You understand what an insulator is. An insulator doesn't conduct electricity, things like glass. What's a semiconductor? Well, it conducts electricity, but not as well as a metal. It blocks the conduction of electricity, but not as well as an insulator. It's somewhere in between. So, what's the big deal? The big deal is that by inserting small numbers of other atoms in a semiconductor, you can dramatically change their electrical properties. More metallic or more insulating. And that's how we make electronic devices, by inserting other elements in specific locations on a semiconductor chip. That's what makes it useful, the fact that you can change its properties easily by doping them. All right, so the technology is, let's see, what are we doing here? Let me start with number 1. I mean, it's really foundational. I don't have to spend much time. Chips are in everything. They're in your cell phones, your laptops, they're in data centers. There are a few thousand in your automobiles. Solar arrays that you see when you drive by outside, that's a semiconductor device. They're in your appliances, they're just everywhere. Life as we know it, I know it because I was born in the 50s. I know what life would be like, but it's powering AI now, and this is what's really driving semiconductor technology. All the AI computations are done with semiconductor technology. And what's happening right now, over the past 50 years or so, AI is an old field. It's recently taken off, but it's been around for a long, long time. If you look back, to the 1950s, the amount of computing that was needed to be done just doubled every 2 years, and that happened according to Moore's law. But something different has happened right now. It's not doubling every 2 years, it's increasing by a factor of 10 every 6 months. Right? And if you look at any of the challenges of the 21st century, anything that we have to address with energy, climate, healthcare, it all is going to rely on digital computing, faster computing, more data, better communication. That means better semiconductor technology. And we've learned that any country that wants to ensure its economic prosperity and ensure its security must be leading in semiconductor technology. That's why we have a CHIPS Act. Okay, so that was a little bit about why it's important. Now, just a little bit about what semiconductor technology is all about. So, before we had semiconductor technology, we used to have devices called vacuum tubes. By the way, Sophie, I actually don't know if I have the right talk here. Could this be, is this the one I emailed you? Maybe I emailed you the wrong one. This is last year's talk, but we can use last year's talk.
Yeah, the date is today.
Pardon me?
The date is today's date.
All right, so I emailed you the wrong talk. That's okay, it's last year's talk. All right, this is a vacuum tube. And you remember these incandescent light bulbs, that we used to have before we had light emitting diodes, LEDs? They had a filament inside them, and you run a current through and this glows. And when Thomas Edison was developing the light bulb, he found that the inside of the bulb got dark over time, and he thought something is coming off of that. Well, that was called the Edison effect. And what was the something that was coming off of the filament? Well, it turned out a physicist in England, J.J. Thomson, discovered that there were electrons that were boiling off of this electrode. It didn't take very long then for someone to make an electronic device with this. So another physicist, Fleming, inserted a plate inside the light bulb and put a positive voltage on the plate so it attracted the negative electrons. And current could flow in one direction, but it couldn't flow in the opposite direction because of that voltage, pulled them one way but not the other. So we had an electronic device that allowed current to flow one way but not the other way. And it didn't take much longer for an American to put a grid in the middle so that you could control the flow of electrons from the filament to the plate. If you apply a negative voltage on the grid, it pushed the electrons back to the filament, and you had less current coming out from the electrons that were collected on the plate. So you could amplify. You could put a small voltage on the grid, and you could make the current that is collected by the plate go up and down, and you had an amplifying device. So this was a really big deal. Suddenly, you had what was called the golden age of radio. You could sit around in your living room, you could listen to music, you could listen to the president giving a fireside chat. It was a really big deal at the time. People began to build digital computers in the mid to late 1940s. The first ones were built with these devices called vacuum tubes. And quite a lot, 17,000 vacuum tubes. It took a lot of room, it weighed a lot, and if you remember, these light bulbs burn out. Something like 50 or so of them burned out every day, and there was someone's job was to run to the back of the machine and plug in a new vacuum tube as quickly as they could so the calculation could continue. So they were not particularly reliable devices. This machine was able to do 500 floating operations per second, 500 flops. Do you know how many flops does a supercomputer do today? The most, trillion, quadrillion, 10 to the, exascale now we're at, which is 10 to the 18th floating point operations per second. That's what you carry around in your pocket is much more powerful than this first computer. Well, so it was widely appreciated that these devices we have to have a better electronic device. We can't carry these big, bulky vacuum tubes. They consume a lot of power, they burn out, they're not reliable. And it was understood, people had speculated about building devices that were all solid. They weren't inside a vacuum. Electrons moved within a solid material, a semiconductor, but nobody had been able to build them until the late 1940s at Bell Labs. And I call this the discovery of the transistor. They were trying to produce a transistor, and they couldn't figure out transistor was the amplifying device that replaced the vacuum tube. They were trying to build one that had been patented in the 1930s, but nobody had been able to realize it. And they couldn't make it work. And they stumbled on a different effect, and they made a different kind of transistor. So they discovered, it was a discovery, it really wasn't an invention. And you can see this is a reproduction model of the first transistor. So, and looking at that, you probably wouldn't have predicted it would change the world. People think this is the most important invention of the 20th century. There was a little article about it in the New York Times, buried somewhere deep in the, nobody thought it was a particularly big deal. But you can see the semiconductor slab down there. It was germanium was the semiconductor. And there's some interesting Purdue history. The reason they chose germanium, because in the physics department here at Purdue, where's the physics department? Over this way? The physics department was a leader that way. Okay. They were leaders in semiconductor technology in the 1930s and 40s. And they developed techniques to grow high purity germanium crystals and dope germanium crystals. So when Bell Labs had to pick a semiconductor to use, they picked germanium. It was the most developed semiconductor that there was. Okay, so it was really important. There's some interesting videos you can see. There's lots of interesting history about this and challenges. Who are these three people? The two people standing are the two people that actually invented this transistor. And who's the guy sitting down there in the middle? He's their boss, right? But he was actually a really, really smart person. And he was kind of miffed that he knew these two people were going to get a Nobel Prize. And they worked for him, right? And he wasn't. So shortly after that, he was at a conference in Chicago, I believe. He locked himself in the hotel room for it was a week-long conference or something, and he just got to work and he invented an even better transistor. And that's the one that ended up being manufactured, so they gave him a Nobel Prize too. All right, now, very early, people started making use of these devices. So they were transistors. They were these things, right? And so, okay, they weren't particularly good electronic devices, but you could do things with them. Like, you could make a portable radio. You couldn't carry around a vacuum tube radio. It was big and bulky, and it had huge batteries and everything. This radio was, the transistors in that radio were manufactured by Texas Instruments. So they've been doing this for a long time. The radio itself was manufactured by a company called Regency, I think, located in Indianapolis. And it sold for about $50, which I understand in today's dollars is about $400 or so. So it was fairly expensive, but it wasn't very good. It wasn't a big hit in the market. But not long afterwards, there was a big hit, a big commercial success. It was the Sony shirt pocket radio. It had 6 transistors like this in it, and its audio quality was pretty good, and it was small enough you couldn't quite fit it in a shirt pocket. But this Sony was a good marketer. He had the shirts of his salesmen specially made so they had slightly larger shirt pockets, so they could go around and talk about this cool radio that you could carry around in your shirt pocket. This was a huge commercial hit. And I'm old enough, I can remember when this happened. It was really neat. And then your friend down the block would get an 8 transistor radio, and that was even better. So you had to get a 12 transistor radio. And very early on, we started measuring the power of an electronic system in terms of the number of transistors that are inside it. And that number is still increasing. All right, now, some other interesting things happen. So I tell people it's almost impossible to overstate the importance of this technology. Do you know who Isaac Asimov was? Anyone? Yeah. He was a very famous science fiction writer. I think he passed away a few years ago now. But he made this comment. Something happened that was the most important moment, he said, since mankind emerged as a life form. What could that possibly be? All right. Well, it was something called the planar process. What the heck is that? Well, it was invented by this fellow Gene Horney at Fairchild Semiconductors. And what this is this is the technique that was first invented to make better transistors, but was quickly realized that we cannot just we don't need to make an individual transistor and then put it in a package and then connect up all these wires together. We could take a single piece of silicon, we could make many transistors, and we could connect them all at the same time. While we're manufacturing the transistor, we can manufacture all the wires and we can complete the circuit. That's called an integrated circuit, because everything is integrated together. It's not discrete, and it's all built at once. And Robert Noyce, who was the CEO of Fairchild Semiconductor, led the team that did that first integrated circuit in 1960 using Horney's process. Right? So that was pretty cool. And what drove this industry, it was a very fledgling industry. Things were just getting started. They couldn't do the highest performance electronics, but they could make it really small. Who needed really small electronics? NASA needed really small electronics because they were shooting satellites up and they were trying to go to the moon. And NASA was the biggest market for this technology, and that's what allowed it to grow. That's who they sold their first chips to. And many people will say the reason that we beat the Russians to the moon is we had onboard computers because we had transistors, and I don't think they did. Is that right? Okay, my colleague back there is confirming it. So, what's a transistor? So this is, if you look inside this little thing I have, today most of them are made on silicon, not all of them. And if you take a cross-sectional look at this through a micrograph, this is the transistor that the people at Bell Labs were trying to make and couldn't when they stumbled on the other transistor. But this is a better transistor. This is what most transistors manufactured today are silicon MOSFETs. So it's got 3 terminals, and they're very descriptive. The source is a source of charged carriers, negatively charged electrons, or entities we call positively charged holes. The drain is where they drain out. And there's a terminal in between called a gate. And you maybe apply 0 volts to the source, you apply a voltage to the gate, you apply a positive voltage to the drain, and the positive voltage wants to attract electrons and pull them across. But they can't get across unless you apply the proper voltage to the gate, and you either open or close the switch. So it's a very simple device. That's how it works. It was demonstrated again at Bell Labs in about 1959, and it was demonstrated by a Purdue alum, a mechanical engineer by the name of John Atala, who became a really good semiconductor physicist after he left Purdue and joined Bell Labs. So there's a lot of Purdue history in all of this. One of the things he did is, you can see there's a very thin insulating layer between the metal gate electrode and the silicon surface. And John Atala was the one who discovered how to make that thin insulating layer in a way that it tied up all of the defects on the surface. That was the reason nobody could make these devices since they were invented in 1930. There were so many defects on the surface of a silicon crystal. And he discovered that if you put this glass layer on in just the right way, you could tie up all of these defects and you could make the device work. All right, so I should quickly, you should know what the planar process is, because we still make chips this way. And this is the most important moment since we emerged as a life form, right? So we should know about this. How does it work? Well, you maybe take a wafer. P-type means it has positive charge carriers. And we grow or deposit a layer of insulator on top of it. The most common one that was used was silicon dioxide, quartz. Then you put a layer of photosensitive material on it. When we used to have photographic film, this is like a photographic film. Now we have digital cameras. But you put a layer of photosensitive material on it. And then we have a mask, and this is coming out of the page. And it's got holes and openings in it. And it has a pattern that we want to transfer to the wafer so that we can dope it and then make an electronic device. So we have an illumination source, and we shine light. The light goes through the holes. The light makes a chemical change in the resist, and then you put the resist in a chemical that dissolves away the resist that has been exposed to light. And then you put the wafer in a material that etches the insulating layer but doesn't etch silicon. And when you're all done with that, you strip the resist off and you've transferred the pattern from the mask to this insulating layer. Okay? All right, so we have this pattern. We have these holes in this insulating layer, and the wafer is exposed behind it. Now we can introduce dopants. One way to introduce dopants is to ionize them. So this is arsenic, ionized, so it has a positive charge. You put it in a machine that has a big negative voltage on it, and it accelerates them to high energies, and you shoot them into the silicon wafer. This is called ion implantation. Still used. It was invented by Shockley, one of the three inventors of the transistor, but it's still used today. So we shoot these arsenic atoms into the silicon. Arsenic converts the silicon into an N-type conductor. It has an excess of electrons. So this is the doping that changes the electrical properties. Now we've got dopants in the semiconductor. We can continue our planar process. We can deposit metal so that we can contact these doped regions. When we do the metal, it's going to go up and down over these patterns, so then we polish it off, chemically, mechanically polish it so the surface is flat. Then we do another patterning, and we open up holes, we etch away the metal where we don't want it, and we strip that all off, and we've made ourselves a MOSFET. Okay, so now we have our three terminals, we have our source of electrons, we have the drain where they're going out, and we have the gate in between. So that's the planar process, still used today. That was invented by this fellow, Gene Horney, in 1959, and that's what got everything going. Okay, all right, now, what's happened is over the years we've made transistors smaller and smaller and smaller, and that's put more and more and more of them on a chip, and that's made electronics more and more and more and more powerful, right? So what determines how small you can make these patterns? You're exposing light through these holes in a mask. So probably you've had physics courses where you've learned about diffraction, and you put a light through a pinhole and the light spreads and diffracts out. So that diffraction means you can't make an image as small as the hole in the mask because the light will spread out. And yeah, so that's what limits it. The image that you transfer underneath is bigger than you'd like it to be because of this diffraction limit. So that one is supposed to be a lambda. The shorter the wavelength, the less the diffraction is. Right? So if you go to shorter and shorter and shorter wavelengths, you have less and less diffraction, and that's what people have done over the years. They found illumination sources that have a smaller and smaller wavelength. And where we've ended up today, and you may have a speaker coming, I think, from this company. There is a company in the Netherlands that makes a machine called an extreme ultraviolet lithography machine. This process of making patterns is called lithography. It has a very short wavelength of 13.5 nanometers. It's a very expensive machine. The newest machines now cost almost $500 million each. And there's only one company in the world that knows how to make this machine. And these are the machines that all of the companies that make the leading edge, most sophisticated semiconductor chips use to make transistors as small as they conceivably can. All right, so it's all done on silicon wafers. I'm not going to pass this around, but you can see it afterwards if you'd like to. Oops. So this is a 300 millimeter silicon wafer. A really high purity crystal. This is every atom is in place because it's a crystal. There are almost no defects anywhere. It's almost completely pure silicon with no impurities trapped in there. It's probably the most pure material that human beings manufacture in quantity. And this runs through the manufacturing line, and if you can look carefully there, you can see there's a bunch of rectangles. Each one of those is a silicon chip. And that's what a modern day manufacturing facility looks like. So there's a bunch of chips there. Maybe a big chip might be 2 centimeters by 2 centimeters, like an inch by an inch almost. And it's interesting, if you look at a cross section of that thin wafer, if you look down and you look at the bottom there, you can see there's a transistor on the surface of the silicon itself. But when you put 100 billion transistors on a chip, it takes a lot of wire to wire those all up into the circuit you're trying to build. So there's layer after layer after layer of metal that's crisscrossing all over the chip to wire the transistors up so that they perform the function that you want to. Actually, I think it's something like 60 miles of wire on a high performance chip that it takes. Okay, so this led to Moore's law. So if you've seen plots, how many have heard of Moore's law? Right, everybody. And so, I put an end date on Moore's law. And it's sort of, and there are these debates about whether it's over or not. But Moore's law, Gordon Moore, who went on to found Intel, observed in about 1965 or so that, hey, every year, the chips that we manufacture, we were able to put twice as many transistors on the chip as we could the year before. And he predicted that this will continue for a while. I think he says, I think probably a little bit nervous, but he predicted, maybe for 10 years we'll be able to continue to do that. Well, it's actually continued for 60 years now almost. It's slowed down a little bit. So every two years, the number of transistors on a chip would double. And the performance of the electronic system would double. And it didn't cost twice as much to manufacture that because you were processing these wafers in a batch mode. So electronics got more and more powerful and didn't get more expensive, and that's what made everything possible. Here's a significant time in the history of semiconductors. That was my first job out of college. And I was working on a technology called a 5 micrometer technology. That's the length of the gap between the source and the drain. Today, we would call that a 5,000 nanometer process because we measure, 1 micrometer is 1,000 nanometers. We measure things in nanometers now because they've gotten smaller. Well, and we could do almost 10,000 transistors per chip, which seemed like a enormously high number. And I remember my company sent me to a technical conference, and Gordon Moore was giving a talk, and he was well known, at least in the technical community even then. And I remember him saying, we are almost able to put 10,000 transistors on a chip now. What could anyone possibly do with 10,000 transistors? Why should we even do this? And nobody had a good answer, but that's what the semiconductor people did. They just kept putting more transistors on a chip, and lo and behold, people figured out what to do with them. This is a log plot, so you don't quite get the sense that, this is exponential growth. Every 2 years, we had twice as many transistors on a chip, and electronics got twice as powerful. Today, so this is last year's talk. Last year, the current technology was called 5 nanometer technology. So that's 1,000 times smaller than the technology I worked. And it was really hard to make 5 micrometer MOSFETs work at that time. I think TSMC's latest technology now is called 3 nanometer technology. So devices have gotten, well, here this is 1,000 times smaller. The area is 1,000,000 times smaller. Means you can put 1,000,000 times more transistors on a chip than we could. All right, that's Moore's law. But it's getting really, really hard now. For a long time, this was just like a freight train. It wasn't a law. It didn't have to happen. It wasn't a law of physics. But you knew if your company didn't do it, your competitors probably had brighter engineers and they'd figure out how to do it and you'd be out of business. So it was kind of a self-fulfilling prophecy. If we can't figure out how to do this and our competitors do, we're in trouble. And that motivated people to work very hard to do it. And you know, one of the interesting things now is there are these semiconductor companies, but many more companies now are designing their own chips because it's the chips that differentiate your products from your competitors' project. If you're buying commodity chips that everyone is using, it's going to be hard to differentiate your product from your competitor's product. So companies like Apple, Google, Amazon, automotive companies design their own chips because there's more and more electronics in automobiles. So more and more semiconductor people are employed by companies you don't think of as semiconductor companies because there's more and more design going on. Okay, but things are happening. So Gordon Moore, made this prediction that the number of transistors on a chip will double every 2 years. And it's hard just to appreciate that. There's no other industry, I think, where this has happened. So this is a few years old, but some numbers from 2019, they could put 5 billion transistors on a chip. Today we can put 100 billion transistors on a chip. But even at that time, Moore was pointing out that if cars had improved at that pace, they would get 100,000 miles per gallon, right? And it would cost more to park your Rolls Royce than it would to buy it, right? So really, no other technology has progressed over this extended period of time the way semiconductor technology has. So this is the plot he made, and the dashed line said, okay, this will probably continue for a while, but even he had no idea how long it could continue. Whoops, what do I have there? Yeah. So the idea was that early on, if you tried to put too many transistors on a chip, you would have defects in the manufacturing process, and none of them would work. But then when you improved the process, then the next year you could put more transistors on, and they still worked. And then if you improved the process again, then the next year you could put twice as many on, and it still worked. And that's what happened. So the goal became to do something called a system on chip. So the goal of people was to put the entire electronic system on one silicon chip. And that's what drove things for a long time. Okay, so we have these wafers, and after you process the wafers, you dice them up, and you put them in a package. So this one is a few years old, but there's a fairly big chip, I think. And what is that? That's from a Sun Microsystem processor a long time. That's a company that no longer exists. Some of you might have heard of it. And this is kind of a low-tech, labor-intensive industry. 97% of this has been outsourced from the US. We just can't compete in that, and we don't want to. But what's coming now is something called advanced packaging. And these are very sophisticated packages where you put multiple chips in a single package and you put them in such intimate contact that they behave almost as one very large chip. And you can put different chips of different types, all in intimate contact in an advanced package. And this is thought to be the way that electronics is going to progress in the future, because it's getting really, really hard and really, really expensive to put more and more transistors on a chip. We're making them about as small as we can conceivably make them. So this is called system in package instead of system on chip. So that's, many of you, if you go into this industry, you'll spend a lot of time in system on package design. And one example of that is AI. So this is looking inside the package. So the leading supplier of AI chips is a design company called NVIDIA, and they produce the leading AI chips. So when you're doing AI calculations, you need enormous amounts of data, and you have to get the data back and forth from the processor. So there's a package where a set of memory chips, and I think they have 16 layers in this now, is stacked adjacent to the microprocessor inside one of these advanced packages, and is put in such intimate contact that you can get the data in and out very, very quickly. The leading supplier of these high bandwidth memory chips is a company called SK Hynix, which will probably be here soon to talk. And SK Hynix is a Korean company, but some of you may know that they've announced that they're going to be building a factory about 1 mile north of campus here in the Purdue Research Park. So that'll create a lot of opportunities for internships and co-ops and jobs and things, because they're the world's leading supplier of these high bandwidth memory chips. Okay, so we'll continue to have plots like this, but we'll probably relabel them as transistors per package instead of transistors per chip. But the electronics will continue to get more and more sophisticated that way. All right, I want to say a little bit about the industry, and I only have a couple of minutes left. So this is a very broad industry. There's a set of companies that all they do, they're called fabless design companies. They don't manufacture chips, they just design chips. Other people manufacture them. And this can be highly profitable, especially if you're a company like NVIDIA, because you're making these very sophisticated chips that you can sell for an awful lot. I think NVIDIA has the largest market cap of any company in the world right now. You don't need to make your own chips, right? Then there's a set of companies called foundries. They don't design chips, they just manufacture chips that other people design. And the world's largest foundry is this company in Taiwan called TSMC, but there are others. Global Foundries in New York. Intel is getting into the foundry business. And then there's a group of companies called outsourced assembly and test. They do the packaging and the testing. And that's an industry that's mostly been outsourced from the US also. Now, on each one of these, so the fabless design companies, here are some, you may have heard of AMD, NVIDIA. Tesla designs its own chips for its automobiles. They don't make their chips, but they design them and other people fabricate them. There's a whole set of companies, and some of them will come here. And some of these are very big companies that produce the sophisticated design tools that these companies use to design their chips. So companies like Cadence and Synopsys and Mentor Graphics. Now on foundries, TSMC in Taiwan is the largest. Global Foundries is in New York, it's a big one. Intel is getting into the foundry business. They're opening a factory in Ohio that will be in the foundry business. And there's a whole nother set of companies that just support foundries. So Applied Materials makes these sophisticated tools that the factories use to manufacture chips. ASML is that extreme ultraviolet lithography tool. There are chemical companies that supply the chemicals and the materials. And there's a whole industry that just supplies the foundries with what they need inside their factories. And then there's outsourced assembly and test also. And there are some less well-known names because almost all of those have been outsourced to Asia. We hope to bring some of that industry back to the US when we go to much more advanced packaging. Okay, and there's a set of companies also that are called integrated device manufacturers. They do everything. They design their chips, they manufacture their chips, they package their chips. And these are some of the companies that are integrated device manufacturers. Okay, now I just want to mention, so some of these companies shared some of their data with us. And the point I want to make is that if you look at this, if you look at the fabless design companies, they employ a lot of electrical engineers and computer scientists and computer engineers. But if you look at the foundries, they employ a lot of materials engineers, chemical engineers, mechanical engineers. If you look at the tool manufacturers, there's a lot of mechanical engineers, materials engineers, industrial engineers. If you look at the materials companies, the ones that supply chemicals and wafers and other materials, they're probably heavily materials engineers, chemistry grads, chemical engineers. So there's really a wide variety of whatever your degree is, your STEM degree is, there's a place for you in this industry. The other thing I'll point out is that of the engineering jobs, a little over half of them are for graduate degrees, and both at the master's and at the PhD level, but there are large numbers of opportunities for BS degrees as well. So lots of opportunities. All right, so let me summarize. All right, this is a really important technology. You know, whatever you aim to do, whatever you end up doing, you're probably going to rely on semiconductor technology to get it done. So having an understanding of this industry is very worthwhile. It's more and more powerful. AI is driving it now. And it's just going to be hard for the semiconductor technology. It has this insatiable appetite for more computing and more data. How are we going to keep up with that? You're going to have a lot of fun figuring out how to do that. And it's going to be fun. You know, this is a field that's driven by industry, by innovation. I mean, you continually need to be reinventing yourself and moving to the next generation of technology, or your competitors will. But it's getting more and more diverse because this technology is used in more and more places, not only in cell phones and data centers, but digital agriculture and health and medicine and everywhere. Universities have an important role to play. So this is an industry that will grow in the US for probably decades to come. If you ask the CEOs of these companies, what's your number one challenge in getting this done? They all give the same answer. It's, where are we going to find the people? Where are we going to find the talent? We're tripling the number of factories that we have in the US. So it's good to consider as you're thinking about, you have lots of opportunities in this field. Okay. So yeah, lots of exciting and important career opportunities. So the future is bright. All right, so I'll just, I'll stop there. I think I've run a little over time. I'll hang around. I tried to cover the whole ecosystem because every week you're going to have one of these companies come in, and I hope this helps you figure out where they fit in the whole ecosystem. It's a fascinating field to get involved in. It's going to be a great course, I think. So good luck in the course. Good luck in your semester. Thank you. Thanks.